In your introductory chemistry course, you're going to encounter two chemical bondings. And the very first one would be an ionic bond, and the second one will be covalent bond. In this particular video, we'll cover the ionic bond. Let's begin. What is ionic bonding? Let me illustrate by showing you sodium and chlorine. These both are neutrally charged. There is no attraction between them. Well, the sodium and the chlorine somehow, we'll talk about that later, somehow gains or loses an electron in order to become a charged ion. Sodium positively charged and chlorine negatively charged. The attraction between the negative and the positive allows the sodium and chlorine to come closer together because of that attraction. The attraction forms into this compound, also known as the ionic compound. So in other words, this ionic bonding that's going on here is a type of a bond or type of a linkage that is formed by two different charges. There are two electrostatic attraction due to the positive and the negative charge that will come close together to form a bond. Ionic compound, this in itself, this entirety is considered to be a sodium chloride, and that is a compound. It formed into a compound. So we have an element and an element that became ions. The ions then came together to form a compound. And that attraction between them two is the ionic bonding. The ionic bonding is not just limited to just them two, but rather it could be attracted to multiple of each other, forming a solid like this. Your typical table salt won't be just sodium and chlorine, just that two together, but rather a big giant clump like this. Now, how does this ionic bond form at a very small, minuscule level? So let's see. Here's my sodium, neutrally charged. Here's my chlorine, also neutrally charged. The very outermost layer right here, this is called the valence electrons. So there's valence electrons for sodium, there's valence electron for chlorine, which is in the very outermost layer. Now, I know that the sodium has a special, it says it's special electron because it's in red. It's not that it's special in per se. I just want you to see the next step, which is that the sodium will donate its electron to the chlorine. So and the chlorine will accept that one electron. That causes one electron less for the sodium. One electron less, that means a positive charge will form. Now chlorine has one electron more, so they become negatively one charged. If the sodium were to donate 2, then it will be sodium 2 plus. If the chlorine were to accept 10, then it'll be negative 10. But here we're only working with one electrons being transferred from sodium to chlorine. This causes a positive and negative charged ion, and now there could be an attraction, the electrostatic attraction. So ionic bonding works hand in hand with the metal, which is the sodium, and the non-metal, which is the chlorine. All ionic compound will consist of a metal and a non-metal. The first will be the metal, and the second will be non-metal. Let's do a learning check. Which of the following are ionic compounds? First one is made up of a non-metal and a non-metal. Though it is an ion, but it is not an ionic compound because it is made up of non-metal and non-metal. Second one, so I should write that down. Not an ionic compound. Second one, sodium is a metal, phosphorus is a non-metal. So this is. And lastly, this is also an ionic compound. Now, the next question is, well, why do some atoms donate and some accept? How do we know which one's going to donate and which one is going to accept these electrons to form an ion? And let's add another factor. How do you know how many to donate and how many to accept? How do these elements know that? Well, let's look at an example of magnesium and chlorine. Here's magnesium. Its valence electron is 2. Chlorine valence electron, there are 7. So does this chlorine. Now, they are going to want to, their desire is to fulfill their outermost shell, their very outermost valence electron to have totality of 8. Except for hydrogen, they want 2. Now, having 8 electrons allows a valence electron to be full, and that gives it a stability for the element. So let's look at chlorine. It's got 7 right now. How many do they want in order to get 8? Yeah, they're just going to want 1 more. So right now, valence electron in this for chlorine, there are 7. So is this one. So you just need 1 more in order to gain this fulfilled octet, or also known as the octet rule. Let's look at magnesium. Currently, the valence electron is 2. Now they can gain 6 more in order to fulfill the octet. But they could also just lose the 2. If they lose this 2, they may lose this entire valence row, but the next row over will have totality of 8. 1, 2, 3, 4, 5, 6, 7, 8. So now this magnesium has achieved its octet rule because it has donated the 2. The outermost layer has 8. So this is how we know which one will donate and which one will accept. It's finite which one's easier to get to the octet. So in order to form an ionic bonding, the magnesium will donate one of the electrons to the chlorine and the other one to the other chlorine, forming a positive 2 charge for magnesium because they donated the 2 electrons. And chlorine, they accepted 1 electron each, so they become -1 charge. -1 charge, -1 charge, and positive 2 charge. Opposite charges, so they are going to attract each other, forming an ionic bond. And now forming an ionic compound, magnesium chloride. Now I'm showing you an image of the periodic table, and this is because I want you to see that it is the trend of why certain rows, certain columns has certain charges really depends on this octet rule. The atoms, they want to be like noble gas. What does that mean? It means that they want to have 8 electrons in the outermost layer. That's because all of these noble gases from helium and on, they have 8 electrons around their valence electron. The valence electron is 8, so they want to be like them. Okay, and fulfill the octet. So, column 1. Column 1 likes to lose an electron, so having +1 charge. Losing 1 electron allows them to become the noble gas before, which is helium, neon, argon, and so forth. What about column 2? From beryllium and on, they have the tendency of +2. They want to lose that 2 electrons in order to show that they have 8 electrons in their very outermost layer. We've seen that in the magnesium case in the previous slide. Then the row 3 will have positive 3 charge, and that's because they want to lose 3 electrons to become noble gas. Now, it's a little different from coming from the right. From the fluorine, the halogens, they want to gain 1 more to become noble gas. So hence negative 1 charge, next negative 2, and then negative 3. There is this tendency of all of these elements when they become an ion to have these charges so that they can fulfill the octet rule. Let's do a learning check. It's a state the charge each element typically gets as an ion. Does the charge indicate they have lost or gained electrons? Let's look at sodium. Sodium is located here, so their tendency is to have +1. So the charge tendency is +1. Having +1 means that it has lost 1 electron. Let's look at phosphorus. Phosphorus is located here. Phosphorus is under the row where it has negative 3 charge. Negative 3 charge. That means it likes to gain 3 electrons so that it will have totality of 8 electrons around the valence electron shell. Calcium +2. It's located here. So they have lost 2 electrons in order to fulfill its octet.